All right, so section 8.3 we're not going to cover in its entirety. It's actually a short section anyways, but the more in-depth study of these things that we call isomorphisms is typically left to a second course in linear algebra. We're going to talk about the definition of what an isomorphism is, and I want to just briefly talk about it in a more general context, because this is a term that applies to far, far more than just linear algebra and vector spaces. So let's just start with the definition. A linear transformation T that maps V to W is called an isomorphism if the linear transformation is both 1-to-1 and onto. And I mentioned this in the previous section in 8.2. But if this is the case, if this linear transformation is an isomorphism, then what we say is that the two vector spaces V and W are isomorphic. Now, when we talk about isomorphisms, the isomorphism says more about the relationship between the vector spaces themselves than it does about the function that defines it. And this is a perspective on functions that takes a little bit of getting used to for students of mathematics that start at linear algebra and go on from here. Because prior to linear algebra, you haven't really dealt with functions that take inputs from one set and maps them to outputs that can belong to a completely different kind of set. You know, functions that take matrices and produce polynomials from them, or take, you know, general functions and map them to ordered pairs or something like that, right? Prior to that, you always look at functions that map R to R or Rn to Rn, right? If you've been through Calculus 3. In higher mathematics, in particular in areas of math like abstract algebra, which you can kind of say linear algebra sort of fits into that same category as abstract algebra, we very commonly look at functions that map one type of set, or what we call an algebraic structure, into a different algebraic structure. So again, if you study math beyond this course and you end up like majoring in math, for example, if you take a course like abstract algebra, you're going to study other types of algebraic structures. Vector spaces are one kind of algebraic structure, but you have things called groups, rings, fields. Those are the three that you would study in like a first course in linear algebra. There's lots more than that. Semigroups, quasi-ring. There's all sorts of different things you can kind of get into. But for any one of those types of algebraic structures, there is a concept of this thing called an isomorphism. And it's always defined in a very similar way. You have both 1-to-1 and onto as properties of that function that defines this thing. And then you have something called an operation preserving property. For us, that operation preserving property is what's called a linear transformation. That's what this is in the context of vector spaces. But it takes on a slightly different form in the cases of groups, rings, fields, all of these other algebraic structures. And it really all boils down to what kind of operations are you allowed to perform on that algebraic structure. For us, it's vector addition and scalar multiplication. But those operations can look different on different algebraic structures. Okay, so this is all probably very vague, very abstract, because again, it's talking about topics that aren't really a part of this class, but very closely related. Now, like I said, an isomorphism, even though it is a function mapping one type of algebraic structure into another algebraic structure of the same type, in this case, vector space to vector space, the isomorphism establishes that these two vector spaces are, in a sense, algebraically identical. And I'm going to be a little bit more specific about what I mean by that. But let's start with an example to sort of help make that a little more concrete. So I want to show that M22 is isomorphic to R4. And what it means to show that those two vector spaces are isomorphic is it's to show that there exists an isomorphism between them. We've actually done that already. We defined this vector, or this linear transformation, in the previous section, A, B, C, D. That equals A, B, C, D, is an isomorphism And we know this because in that section we showed that this linear transformation is both one-to-one and onto. So that's all we need, and we took advantage of the fact that it's a linear transformation without showing it explicitly. So we would also need to show that, but we've already basically done the work to show this. So that's great. What does that mean, though? Well, and as far as vector space structure is concerned, the existence of this function in the first place is showing that the vector space M22 is algebraically identical to the vector space R4. Now, what do we mean by that? Well, pick any two matrices in T or in M22. So, for example, A1, B1, C1, D1, and let's add them. A2, B2, C2, D2, right? Well, we know that the sum of these two things is just A1 plus A2, B1 plus B2, C1 plus C2, D1 plus D2, right? Now, let's look at the image of these two matrices under this isomorphism. So if I map each of these to the corresponding vector in R4 under this linear transformation T, I get A1, B1, C1, D1. Remember, that's what the linear transformation does. It takes these entries, maps them to these coordinates. Okay? A2, B2, C2, D2. So when I map these things to these functions, these ordered four tuples, if I were to add these ordered four tuples using the addition that's defined on R4, I add component-wise A1 plus A2, B1 plus B2, C1 plus C2, D1 plus D2, right? So notice that the result of the addition here gives me a vector that's the image of this vector up here. And isomorphisms, because they're one-to-one, I can reverse this image to get the inverse function, and it would send me right back to where I started from as well. So basically what this is saying is that each of these matrices can be thought of as ordered four tuples, and the operations that I perform on these correspond exactly to the operations that I would be performing on their representatives in the matrix space M22. So I could do a similar argument with scalar multiplication as well, but what this is showing is that even though these things appear different than these, as far as the operations that we define on vector spaces are concerned, all of these are really just representatives of vectors in R4. So I can think of anything here as a vector in R4, and there's no loss of information by doing that. Okay, so that's what an isomorphism is it's showing that these two vector spaces, which seem very different, are in a sense really the same thing. We're talking about the same thing. Now, that's one case of an isomorphism. But the point of going into 8.3 at all, I was originally going to skip this section, but the point of going into it at all is to establish this extremely, extremely important result in all of linear algebra. This theorem which says that every real n-dimensional vector space is isomorphic to Rn. All of them. M22 is a four-dimensional space. A basis for this would be the standard basis for M22, which we know has four vectors in it. So this has dimension 4. But you know what else has dimension 4? Is the polynomial vector space P3. We know that that has dimension 4, and this theorem would say that P3 is also isomorphic to R4. Much more powerfully than that, if I look at any vector space, and by saying real, I'm saying that the scalar field that we're allowed to use is the real numbers, but any vector space that has a finite dimension of n is going to be isomorphic to Rn, which basically means that as far as finite dimensional vector spaces are concerned, Rn, for any value of n, is the only actual vector space that exists. algebraically speaking, because any others, whether we look at them in the forms of matrices or polynomials or whatever, those are all going to be algebraically identical to Rn anyways. So why is this? Let's go through this proof. Let's let V be any n-dimensional vector space. And what we're going to do is select a basis, an ordered basis for S. For V, and I'm going to call it S. Because V is n-dimensional, there should be n vectors in here, V1 through Vn. Now I'm going to let U be any vector in V, but because I've defined this basis here, I can represent U as a linear combination of these basis vectors. So U equals K1V1 plus K2V2, blah, 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 right? I'm going to pick another vector in V. I'm just going to call it V. And do the same thing, represent it as a linear combination of those basis vectors, D1, V1 plus D2, V2, and so on. And then I'm going to let C just be any scalar. Okay, now T, I'm going to define this function T that maps V into Rn to be the coordinate map. And we've talked about these before, but remember in chapter 4 where we talked about coordinate vectors, it's just a coordinate vector is just the vector in Rn that maps a vector to the vector in Rn that uses these scalars on this linear combination as its coordinates, right? So the goal here is to show that this coordinate map is an isomorphism. Because if it's an isomorphism, what it's doing is it's mapping the vector space V into the vector space Rn. That's where these vectors here live, right? If I can show that's an isomorphism, then that would mean that V is isomorphic to Rn. And because V is an arbitrary n-dimensional vector space, this would be true for any n-dimensional vector space. So in order to show that it's an isomorphism, we have three things that we actually have to show. We have to show, first of all, that it's a linear transformation at all. Then we have to show that it's both one-to-one and onto. So to that end, to show that it's a linear transformation, we need to show that it has that additive and homogeneity property. So the additive property, T of U plus V. Well, if I'm adding U plus V, U and V were given up here in the form of linear combinations of the same basis vectors, V1 through Vn. So if I'm adding these, I can add basically by combining like terms, K1V1 plus D1V1, or factoring the V1 out, looks like K1 plus D1 times V1. And same for all the other coordinates. So now what I have is a linear combination, or I have a function T, we don't know that it's a linear combination yet, of a vector that is given as a linear combination of those basis vectors, V1, V2, all the way through Vn. What does T do to those types of vectors? Well, it maps them to their coordinate vector in Rn, meaning it takes the scalars in this linear combination and makes them coordinates in this n tuple right here. Now, K1 plus D1, K2 plus D2. Because this is a vector in Rn and we have vector space structure there, we know that this is the sum of these two vectors in Rn, K1 through Kn, D1 through Dn. This would give us this. However, this is the coordinate vector for U, because these are the scalars that show up in that linear combination, and this is the coordinate vector for V. So this is just T of U. Remember, T of U gives me that coordinate vector, and this is just T of V. From here to here, I see that I have that additive property that we need. Similarly, for homogeneity, if I wanted to find T of Cu, remember C is just some scalar. Well, multiplying C to U is the same as multiplying C to its linear combination in the basis S. So that would look like C K1V1 plus C K2V2 and so on. Now, mapping this to its coordinate vector in Rn, now the coefficients, instead of just looking like K1, K2, and so on, they look like CK1, CK2, and so on. So that becomes the coordinate vector. But because C shows up in each one of these, the C can be brought out using the scalar multiplication that's defined on Rn. So this is equal to C times the coordinate vector for U, which can be written this way, C times T of U. Again, homogeneity. The C is able to be brought out. So that means that T is a linear combination. Okay, T is linear. Now, let's prove the rest of this. Remember, I said there's three things to prove. We need to show that T is a linear combination. We just did that. And now we need to show that T is 1-to-1 and onto. Now, we showed in the previous section in 8.2 that if the two vector spaces that you're working with have the same dimension, it's enough to show that the linear transformation between them has a kernel of the zero subspace. The kernel only contains 0. We showed that under those assumptions that the linear transformation would be both 1-to-1 and onto. So to that end, let's let V be any vector in the kernel of T. So what does that mean? Well, that means T of V should be the 0 vector in Rn, which looks like this. But in the context of this linear transformation, what does this mean for the vector V? Well, this would mean that the zeros here are the scalars that show up on the linear combination of the basis vectors that give us V. So in other words, V is equal to 0 V1 plus 0 V2 plus all of that. We know from the basic properties of the 0 scalar for vector spaces, 0 times any one of these is equal to the 0 vector in V. And their sum would also be the 0 vector. So that means that the kernel of T only contains the 0 vector, which means T is both 1-to-1 and onto, making T an isomorphism. Therefore, V is isomorphic to Rn, where V can be any n-dimensional vector space. That's extremely, extremely powerful as a result, and one of the major theorems of linear algebra. Because again, what it means in the context of the algebraic structure of these vector spaces is that they're all basically identical to Rn. And Rn is a very familiar environment to be working in, especially when it's R2 or R3. We can visually represent those vectors in the plane or in three-dimensional space. So that means, and we're not going to go this deep with it because again, this is better left for linear algebra. This means that especially when we start introducing inner products into these vector spaces, inner products, remember, give us a concept of distance, norm, angle between vectors. It basically gives geometry to vector spaces. That combined with this theorem basically shows us that we can think of other vector spaces geometrically in a manner that's identical to the geometry that exists on Euclidean space, R2 and R3. Really, really powerful result. But we only use a little bit of the consequences of this result in this class. It's just an introductory class. So to wrap this section up, because this is all I really wanted to cover was this theorem, I just want to mention a couple of spaces that we know are isomorphic and give names to their isomorphisms. So the linear transformation that maps T that maps M22 and R4 that we talked about before, this one takes this matrix ABCD and gives us the ordered four tuple ABCD. We call that the natural isomorphism. We already talked about why it's an isomorphism at the beginning of this video. But it's the natural one because it sort of makes sense. Assign entries in this matrix to coordinates of this vector. We don't do anything fancy with it. It is not the only isomorphism between M22 and R4. There are lots and lots of other ones. In fact, another isomorphism would take a matrix ABCD and assign it to the vector DCBA. I can reverse the order, and that would actually also be an isomorphism. It's easy to show that. But we call this one the natural one just because it's the most natural one, right? Another natural isomorphism that takes Pn into Rn plus 1. Notice the dimension of these is the same. If you plug in the polynomial a0 plus a1x plus, all the way until you get to an x to the n, if this thing strips this polynomial of its scalars and then puts the scalars into an ordered n plus 1 tuple, this produces an isomorphism as well. It's the natural isomorphism because it's basically all it's doing is it's taking the scalars, which are what make this polynomial in here unique, and then assign them to a vector with the exact same scalars in Rn plus 1. That's the natural isomorphism. Usually you can kind of tell when you're working with a natural isomorphism. So that's going to be it for 8.3.